so we have determined that UQSL2 is a quotient of the double of BQ. And so now we know we want to compute the R matrix. So to compute the R matrix of the double of BQ, we need a basis of BQ and its dual basis. So, and we need to compute the dual basis of the usual basis of BQ. So the basis, so let's call Fij of C, which is dual to the basis EIKG of BQ. So it is computed as follows. So we need to define the linear form. So on, let's say, EK. Okay, so there is a formula. I give the formula. C1 to the n. So we know, okay. So A equal to 0 to n minus 1. So here I put Q minus I minus 1 over 2. I divide by factor I. This is non-zero because I is less than n minus 1. Q minus 2 AI plus G beta I alpha A. Okay, let us check this. Let us check this formula. So we need to compute this. Sorry. Here, sorry. I just did so. So we need to compute. If I evaluate this formula, so 1 over n sum A equals 0 to n minus 1. I minus 1 over. So I need to evaluate beta I alpha A I E K K L. I want to compute this number. And I need to find delta I K, delta GL. Okay. So So we have a formula. Remember the formula star was to compute the product of two forms. So it is the sum here from B to equals 0 to k, q b, k minus b, k b of the first form beta I e k minus b kl alpha j e beta k plus l minus b.
So using alpha A?
Alpha thanks A. Alpha A. Okay. That's because of the formula star. Now we know this. So we have seen so by this is so I have indicated that we can compute this by induction, and so I gave the formula for a power of alpha. So delta B0 Q 2A K plus L minus B, but B0, K plus L. And this one, it is delta K minus B should be equal to I. And we find I minus 1 over 2 factor L I. Okay, so now there is some simplifications. So here in this sum, we need only B equal 0. So here we have delta Ki. 1 over n, sum A equals 0 to n minus 1. So B is 0. Here, so this coefficient cancel. Here, what do we have? So B is 0, so this cancel. So what we have? Q2I plus J Q2I K plus L.
Is it minus Q the first one?
But K is I. K is I. So what is 1 over n, sum A is 0 to n minus 1. So what do we have? The I, so we have Q2 L minus G to the A. But 1 over n sum k equals 0 to n minus 1. So let's say A z to the A. What is it? We know to compute this. It is just 1 if z is 1. It is z to the n minus 1. So 1 over to z minus 1 if z is different of 1. But this 1z is a root of unit. It is 0. So k2l minus 1, so this is and root of 1. And because L and J are between 0 and n minus 1, Q2L minus G is 1, if and only if K is L is equal to G. Because Q is primitive nth root of 1, and n is odd. We have Q2n minus G is 1 if so this is clear. So we need that n. So I can put one more. This is equivalent to n divided 2l minus j, but it is equivalent to this. Because L and J are between, L minus J between negative n minus 1 and n minus 1. So and n is odd, so n should, I should maybe add, so n divide n minus g, which is equal to this. Equivalent. Okay, so an easy computation. So what do we obtain? This is non-zero only when L is equal to j, and when L is equal to j, it is equal to 1. So we have delta chi I delta Lj. And this proves that, and this is Fij of Ek Ka, because these are dual bases. So here we prove that the formula for the dual basis of this one is here. Okay, so now we are done, almost. So, what do we have? The R matrix of D of BQ is by definition, so we take EI KJ, comme ça, Fij. And so the R matrix of D of QQ bar SL2, so which is D of BQ divided by K is alpha. And the other change is so beta is, I do not remember. Beta is Q minus Q inverse over Q square Fk. We made this change of variable. So I compute it here. Okay, so this remains, and I repass Fij using the formula. So it is R. So we have a double sum. 1 over n sum Ig to n minus 1. Here also it is n minus 1. Ig and A between n minus 1. So we have the coefficient Q is I minus 1 over 2 Q minus 2 A I plus G. So EI Kj. So beta is this one. F Ki. Alpha is K. Okay. Well, here is the arithmetic. So we just rewrite a little. So now we have Fk to the I. So is some coefficient f to the I, k to the I, and the coefficient, it is using that kf is q negative 2 fk. So this coefficient is computed as, so I have it, fk to the I is what you find. It's an easy induction, q minus I minus 1. Okay. So here we have 1 over n. So here we have q inverse to the I over factorial I, and we have a big power of q minus I minus 1 over 2 minus 2a I plus g minus I minus 1, and here there is q minus 2i. I kg, so ei fi k a plus I. Now, finally, I will replace a plus I by k. And so we found this. So Q is Q inverse to the I. Okay. So the I, so negative minus 2i minus 2 A is k minus I I plus G, EI KG, FI KK. Okay, and now we just need to simplify a little here. And so what is it? Minus 3 half I squared plus 3 half I minus 2I minus 2 Ki minus 2 K J plus 2I squared plus 2ij. So I square, what remains? So 1/2 minus 1/2 I minus 2 K A plus G. Oh, yeah, I will write like this. 2, maybe it's better to 2 plus 2I. So 2I J minus K minus 2 KG. And so this is 1/2 I minus 1. Okay. And finally, we have the R matrix. And so we found, let's say, theorem. So R is 1 over N. So what do we have? Q minus Q inverse to the I divided by factorial of I. Q 2. So I minus 1 over 2 plus 2I G minus K minus 2 GK E to the I K to the G tensor F to the I K to the K is an R matrix for U, Q, SL2 bar. And if you make n going to infinity, you will get, and if you complete, you get some R matrix for U, Q, SL2. But if you want to. But anyway, for us, it's sufficient for the quotient, finite dimensional quotient. Okay, this was a long work to obtain this formula.
Sorry, you said we can go to infinity like this becomes an R matrix or you can.
Yeah, but you have an infinite sum, so you have to
Do something.
Yeah, to make a completion, but we do not need to do that. Okay. Now we will find, using this R matrix, a solution of the Yang-Baxter equation which gives a Jones polynomial. Okay. So as I explained, if you have an R matrix, it induces the solution of the Yang-Baxter if you have a module. So it's easy to find from two-dimensional module. So now we consider the two-dimensional UQSL2 bar module M. So this is generated by, let's say, U and V, defined by okay, so I give the formula and then I explain. K, let's say U is Q times U. E to the U is 0, f to the u is v, kv is q inverse v, ev is 0, and f v is u. Is it this one? No, sorry, EV is u, F is 0. Okay. So recall we have as the relation are k to the n is 1, e to the n and f to the n are 0, ke is q square ek, kf is q minus square fk, and ef is fk, k minus k inverse. These are the relations. So, if you have a module and take a, you can take, so you take a proper vector for the action of k to the n is 1, it acts as the root of unity, and then if you have such a vector prop and you multiply e by e, you still have a vector, proper vector for k. So using e to the n equals 0, you can assume that for this vector, e is in the kernel of e. And then you denote v, e, f of u, and you make the computation using this relation, you obtain this. And so that's how you obtain a module. And so you can verify easily that it is a module. So this is indeed a module. So what do you have for example to verify that the relations are true? For example, EF minus F E minus K ver minus K Q minus Q minus 1. When you act as U, what do you obtain? FU is V and EV is U. Take U. No. EU is 0. This one is 0. K inverse U. K inverse U is K inverse U. Q inverse U. So minus Q inverse U. Oh. Sorry. So KU is QU. K inverse U is K inverse U. So minus 0 minus. And so what you obtain is U minus U is 0. And similarly for V. And similarly for the other relation. For example, KE minus Q square EK U 0. Okay. So you verify that all the relations are true, and so you have a module. Now we can compute the associated solution CMM of the Yang-Baxter equation induced. The solution is induced by R. So this solution, let's call it S. So I keep the formula of the R matrix. And okay, so S of U tensor U. So I denote this coefficient here, let's say gamma I gk. By definition, what do we have? So 1 over n I put also here. By definition, x to the y, it is sum gamma I k. So you act, the R matrix R act on x and y, and then you flip. So f I k k tensor y I k g tensor x. This is a definition of the solution. By definition, then we can compute S U tensor U. Now, if I put U tensor U, so K to the U, so you have QK, Fi. I erased. So Ku is Qu, Kv is Q inverse V, Eu is 0, Fu is V, EV is U, Fu is 0, Fv is 0. Is it correct?
Yes.
Okay. So now if I take here, x is u. So here you have q to the g, ei. We need I is 0. So I is 0. Otherwise, this relation gives, so because of this relation, I should be 0. So I is 0. And now here, Fi U if Fi minus 1 V. So sum Gk, so gamma is 0. So let's, so gamma I Gk. So here we have Q K plus J Fi, so Fi U tensor Ei U. So I is 0. So this is sum of Gk of gamma 0 G K Q K plus G U tensor U, and we need to compute this. So we have this coefficient. So the sum plus G. So it is gamma 0. So this is I is 0. So what remains? Minus 2 GK. Okay. Plus G minus 2 GK 1 over N. So how to compute this? For example, it is sum for, I don't know, G. So Q to the G. 1 over N sum for K. So I put Q 1 minus 2G to the K. But here we know how to compute this. So Q is the nth root of unity, so it is only worth when n divide 1 minus 2g. But this is possible only when j is n plus 1 over 2. J is between 0 and n minus 1. The only possibility, n is odd, is this one. So it is sum for G, QG delta G n plus 1 over 2, as it is just Q n plus 1 over 2. So here the computation at the end is z Q to the n plus 1 over 2. U tensor U. Okay. So, and you can, I suggest you to compute the other, and I explain what you obtain. What you obtain is the following. Then, so S U tensor V, you obtain Q with similar computation V tensor U. S V tensor U, what you obtain is Q n minus 1 over 2 U tensor V plus Q n minus 1 over 2 Q minus Q inverse V tensor U. And also, so this is S U tensor U. And also S V tensor V is Q to the n plus 1 over 2 V tensor V. Okay. This is exactly the same method, so you use the form of the R matrix, and you obtain these formulas. Okay, so now if I put B is U tensor U, U tensor V, V tensor U, V tensor V, basis of M times M, so this so I can write, I define, so I want to see the matrix in C base B of the solution S. But if I have a solution and I multiply it by a scalar, I still have a solution. So I can here multiply by this one, Q squared, Q minus N minus 1 over 2. And what is a matrix? So U tensor U, U tensor V, V tensor U, V tensor V, U tensor U, V tensor V. What we obtain is the following. Q3, 0, 0, 0, 0, 0. Q square 0, 0, Q square, Q3 minus Q, 0, 0, 0, Q3. So this is what you obtain up to scalar. The solution is this one. And if you compute A inverse, it's quite easy to compute. So you need to invert this and this one. So given is 3, 0, 0, 0, 0, yeah, 0, 0. And the inverse of the 2 by 2 matrix in the middle is Q minus 3 minus Q minus 3, Q minus 2, Q minus 2, 0. Okay, so this is the solution of the Yang-Baxter. The inverse is computed like this. And what you can notice here is that if I compute Q minus 2A minus Q star A is a Q minus Q inverse. What you obtain is Q minus Q inverse for the identity matrix. And this is exactly this Kane relation of the Jones polynomial. So this solution of the Yang-Baxter equation gives the Jones polynomial. Okay, and so this explains the relation between the Jones polynomial and quantum group, which is not obvious from the definition of the Jones polynomial I gave. Okay.
Sorry, is it enough to see that if this is satisfied, then the thing is necessarily Jones polynomial?
Yes, the solution of the Yang-Baxter. So, of course, you need, to find, if you have a solution plus an H, I explain how to obtain, and here you can compute the H, which gives the Jones polynomial. So the solution of the Yang-Baxter, I recall it corresponds to this one, and the inverse corresponds to this one. And the identity correspond to this. And this is exactly the Kent relation. You need an enhanced R matrix. What I mean, you need also H to have an operator invariant, but you can easily compute the H in this case. I have no time, but.
Q squared A.
Sorry?
It's Q squared A.
Yes, thanks. Okay, so next time we will see quantum invariant of 3 manifold. So we were in. So I recall you that we have seen two-dimensional TQFTs via Frobenius algebras, then the Jones polynomial and its relationships with the quantum groups, QSL2. And next, we will define, starting next week, quantum invariant of 3 manifolds.